talk about molecular orbital theory. This is the second of two major theories that we discuss in this chapter. They are completely different theories, and it's important that you compartmentalize your knowledge and don't try and take what you learned about valence bond theory and use it in MO theory. This is the only time during the semester that I'll ask you to compartmentalize your knowledge like that. So, MO theory says that when atoms are ready to form a molecule, the atoms move into close proximity. They have their electrons in their orbitals. But all of a sudden, as they get closer and they get ready to make a molecule, the atoms get rid of all their atomic orbitals, they combine with the other atom, and they make new molecular orbitals. You can kind of think of it like bank accounts. I'm very old-fashioned, and I've been married for 40 years. When Bob and I got married, we took all the money we had, which wasn't much. He had a little bit of cash, I had a little bit of cash. We closed our personal bank accounts. We went to the bank together, and we opened new bank accounts. We opened a checking account and a savings account. They were different kinds of accounts, but they were both joint accounts, and the money in them belongs to us. And that's what's going on in MO theory. MO theory says that atoms and molecules are very similar. They both have nuclei. Atoms have one nucleus, molecules have more than one nucleus. And they both have well-defined energy levels that we call orbitals, where the electrons are positioned. The atoms have atomic orbitals. We've already talked about these, S, P, D, F, and we've already looked at drawing orbital box diagrams and writing electron configurations. Molecules have molecular orbitals. So, MO theory says this: when the atoms come together, two orbitals, one from each atom, combine, and they make two new molecular orbitals that belong to the molecule, not to either of the atoms. They make a bonding orbital where there is electron density between the nuclei, above, below, or on the bond axis, and it stabilizes the molecule when it's full. The antibonding orbital has areas of no electron density. We call this a nodal plane. And this destabilizes the molecule when we put electrons in here. So let's start by looking at the simplest example, diatomic hydrogen. We have one hydrogen atom that has a 1s orbital with one electron in it. We have another hydrogen atom with a 1s orbital with an electron in it. We can think of these two atoms as having their nuclei. They are far apart, and they each have a spherical 1s orbital. Now, when these two move together into close proximity, these two orbitals come together and they combine. And they make two new orbitals. Now, these are the same two nuclei, and I've just transposed them over here. These two nuclei are now here, and this is another view of those same two nuclei. So the first orbital that we make is called the sigma 1s. And this encompasses the nuclei, and it has electron density surrounding and between the nuclei on the bond axis. It also makes another orbital that has two lobes. These lobes have a nodal plane between them. This white space on the paper, there is no electron density in here, so it's a nodal plane. And we have electron density in this area. And this orbital with the two lobes is called the sigma star 1s. So sigma orbitals are bonding orbitals, and they add stability to the molecule. The starred orbitals are antibonding orbitals, and they destabilize the molecule. So now that kind of gives you an idea of what these look like, but we're not going to fuss too much with trying to draw three-dimensional pictures on flat paper. So these bonding orbitals are lower in energy. They fill first, then we fill the antibonding orbitals. And we can draw an electron diagram, an orbital box diagram for the molecule, just like